All right, thanks, Ryan. So today I'm going to be going over how to build an auction app with Beaker. And in this talk, I'm going to be going over not only smart contract development, I'm going to be talking about testing and implementing your contract in a front end. But before, I'm going to briefly talk about why you want to use Beaker in the first place. So why Beaker? So before Beaker, you need to, when you're writing a contract, you need to write a lot of helper functions. You have to manually bother with encoding and decoding all the data you're dealing with. There's no cohesion between your development and your testing. So you have your code base for the smart contract, and then you have a completely separate code base for the testing, and there's no cohesion between the two. And then finally, when you're writing the contract and when you're interacting with the contract, you have to manually manage the state, and it can be a little bit cumbersome, and if you have to do more things manually, it's easier to make a mistake. So Beaker eliminates a lot of those things. And if you want to learn more about Beaker, earlier today, Chris Kim did a talk going over the fundamentals of Beaker. But today, I'm going to be going over how to build an actual smart contract using Beaker. So the first thing I want to talk about is the design, what the app we're going to be building looks like. So this is going to be a fairly basic app. It's going to basically have the owner be saved in the smart contract, and then the owner can start an auction, anyone can place a bid, and then auction lasts for a desired length, and then once that length is reached, the winner becomes the new owner. So in Beaker, we're working with Python, so the first thing you gotta do is import the modules you're using. And here we're importing both PyTeal and Beaker. So Beaker is a framework that sits on top of PyTeal, so we'll still be writing PyTeal logic, but we're using Beaker to help organize and integrate with our testing and front end. Then we also have some other imports for writing files. And then finally, we get started by creating our class. So the class inherits from application, which is provided by Beaker, and this gives us a lot of helper functions and allows Beaker to know that this is a smart contract that we're writing. So the first thing I like to do when running a smart contract is think about what sort of storage you're going to be using in the smart contract. On Algorand, there are a couple of different kinds of storage. Here we're using global storage, which is basically key value pairs that is saved in the application itself. So for our application, we're going to be defining 4 different key value pairs. The first 2 are owner and highest bidder, and these are both going to be saving bytes. So you'll see we have stack type equals tealtype.bytes, and that's telling Beaker that this owner key is going to be saving some value that is the type of bytes. And then we're also, for both of these, we're defining our default values. So the default value for our owner is just going to be the creator of the application, so global.creator address. And then the highest bidder is just going to be empty string, because when we create the application, there's going to be no bids, so we want to use an empty string to signify that there's no bids. And then we have 2 integers being saved in key value pairs. We have auction end, which signifies the timestamp at which the auction will end. So on Algorand, you don't have access to the time during execution, but what you do have access to is the timestamp of the last block in the chain. So we can use that to get a rough estimate of when we want the contracts or the auction to end. And then finally, we have highest bid, and this is going to be saving what the current highest bid is. So any new incoming bids have to beat out this value in order to be considered a valid bid. And now we can actually start getting writing our logic. So the first thing we're going to do is write this pay method. And this pay method is a helper function that we're going to be using in our other methods later in the code base. So what we do here is we decorate it with this @internal decorator. And what this is telling Beaker is that this is an internal method that we're using internally, but our end users aren't going to be directly calling this method, and it's only going to be used within other methods in the contract. So we have that @internal decorator, and then the tealtype.none is specifying that it has no return type. So this is basically a void function. And now we can get into the actual logic itself. So the first thing you can see is we're defining our function with 2 arguments, receiver and amount. And this is going to signify who is receiving the payment and what the amount of that payment should be. And then we are using inner transaction builder, which is an abstraction used to send inner transactions in the smart contract. An inner transaction is a transaction that a contract itself sends, and it sends funds from its own address. So every application you create on Algorand has an application ID, and then the application ID to generate an address that it can spend funds from. So we use this inner transaction builder.execute to define what that transaction should be, because we want to signify that this is a payment transaction. We're setting the receiver and the amount according to our arguments that we pass in, and then we're setting the fee to 0. And we're setting the fee to 0 here so that the smart contract itself doesn't have to worry about ensuring that it has enough algo to pay for fees. Instead, on Algorand, fees can be pooled together. So when you call the smart contract, the fee on Algorand is generally 0.001 algo. But here, whenever we call this inner transaction, we need to send 0.002 for a fee so we can cover this fee amount because we hard-coded it to 0. So now, this is the first actual external function that we're going to be calling, and this is what we're going to be calling when we create the smart contract itself. So we have this @create decorator, and that is signifying to Beaker that this is the method that we want to call when the user wants to create the application. And all we're doing here in this create method is initializing the state. So if you remember, when we defined our global state, we set some default values. This initialize application state function will set those keys to the default values that we defined when setting up our state. Okay, so now this is the first real functionality that end user is going to be interacting with, and this is the start auction function. And this is the function that the owner can call when they are ready to start an auction. So the first thing you're going to notice is on this top line, we have the @external decorator, and this is telling Beaker that this start auction function is an external function that end users can call, and it's exposed in the ABI. And if you're not familiar with the ABI, it's basically a JSON file that tells end users and SDKs what sort of methods are available to call, how to call them, what arguments they have. And so this @external decorator handles all that for you and signifies Beaker, we indeed want to expose this as an external function that can be called. So now in the arguments that we take in 3 arguments here. We have the payment and starting price and the length. And if you notice, all of these types that we're annotating it with start with ABI, and that's because these are ABI types in accordance with the ABI specification on Algorand. You don't really need to know the technical details of how the ABI specification works. Really, the main purpose of the API is to provide these abstractions of types so you can easily work with them in higher level languages like PyTeal and Beaker. So the first thing to mention here is that our first argument, payment, is expecting a payment transaction. So on Algorand, we have atomic transactions, which mean you can up to 16 transactions together. So defining payment as an argument to start auction is signifying when we call start auction, we want another payment transaction to be grouped together with the start auction. And then in our contract, we can use this argument to inspect that payment and get details about that payment transaction. The next argument, starting price, this is pretty self-explanatory. This is going to be the starting price for the auction and signifies what is basically the initial highest bid that a person needs to bid in order to become the highest bidder. So the starting price will signify what the first bid needs to surpass in order to be considered valid. And then finally, we have length. So as I mentioned, Algorand, you can get by looking at the timestamp of the last block. So what we're doing here is passing in a number of seconds that we want our auction to last, and then when the end should be. So now in our actual logic, what we're doing here is the first thing is verifying our payment transaction. So as part of the start auction call, we need to send a payment to the contract so that it is able to spend on Algorand. On Algorand, a contract or any account needs a minimum balance of 0.1 algo, and if you're below that balance, you're not actually active in the ledger, and so we need to fund the contract initially so it's able to send transactions. So the first 2 assertions we have here, the first one is verifying that the receiver is indeed the current application address. And then we're also asserting that the amount is equal to 100,000 microalgo. Then what we're doing is we're setting our global state. So we're setting the auction end. So like I mentioned, we're getting the latest timestamp from the last block, and then we're adding the length to that to signify when the auction should end. And then finally, our highest bid, we're just setting that to our auction price, and that's going to be used in the logic determining what a valid bid will be. Okay, so this is the logic for the bid itself, and this is probably the most complex part of the program. And there's a lot of things going on here. So first, again, this is an external method, so this is an ABI method that you can call externally. And then we are also sending in a payment here, but this time the payment will be the bid itself. So when you want to bid, you call this function, but you also send a payment signifying the amount that you want to bid, and then you have to pass in the previous bidder. And on Algorand, in order to interact with a count or an asset or an app, basically anything that involves reading or writing state on chain, you need to predefine what sort of state you're going to be reading. So here, one of the arguments for this function needs to be the previous bidder, because we might be sending them a transaction returning their last bid. So we need to define who that previous bidder is so we can send them a transaction. Then for our actual logic, we first do an assertion, making sure that we haven't passed the auction end. So this is getting the latest timestamp and making sure it's not past the auction end that we set. And then we're verifying the payment transaction. So we assert that the payment amount is greater than the highest bid, and we're asserting that the transaction sender is of the application call is the same transaction sender of the payment. And now we have some conditional logic. And what we're doing is we're checking if the highest bidder is an empty string. And if it's not an empty string, that means that there was a previous bidder. Therefore, we need to execute a transaction returning their bid. So we have, if the highest bidder is an empty string, we're going to assert that the highest bidder is equal to the previous bidder.address. What this is doing is basically ensuring that the previous bidder we passed in is indeed the highest bidder. And then the function takes two arguments, the receiver of the payment and the amount. So here the receiver is going to be the current highest bidder. That pay function call is going to execute an inner transaction, sending back the previous bid to the previous bidder. And once we do that, we can then update the global state to signify who the new highest bidder is and what they bid. So we're setting the highest bid equal to the amount of the payment that was sent, and then we're setting the highest bid to the payment sender. So now in our global state, we'll update what that highest bid is and who it came from. And this is an iterative process. This function will be called multiple times whenever someone wants to bid. And then finally, we have end auction. So end auction is a function that can be called by anyone, and it essentially triggers the logic that ends the auction and basically resets the state. So first thing we're doing here is asserting that we have indeed passed the auction end time, and then we are going to execute a payment to the owner of the amount of the highest bid. So as an owner, you start the auction, people bid on it. At the end of the auction, the highest bid gets sent to the owner. And then once we pay the owner, we can then set the owner to the new highest bidder. We can set the auction end and highest bidder state values to their default values. So for auction end, this is just going to be 0, and for highest bidder, this is just going to be an empty string. And this is going to basically reinitialize the state to what it was when we first created it, except this time it's a new owner. So that was what the smart contract looks like. And now I want to get into kind of the real value proposition of Beaker, and that is what's called the application client. And the application client provides abstraction for actually interacting with a smart contract. In this case, I'll first be going over with how to use the application client for testing, and then we'll be going over some integration on web as well. So first, let's talk about what our end goal for testing is going to be. So we want tests that are reproducible, quick, and simple. And as I mentioned earlier, before Beaker, it was hard to really get that simple is really the key thing that we're adding here with Beaker. And as you can see here, we run these tests that are using Beaker, using PyTest, and we have 15 tests that passed in 0.82 seconds. And this is all because Beaker automatically connects to the underlying local network. So if you start up a network using Sandbox, automatically connect to that. And if it's in dev mode, it'll execute instantly, and you have super quick testing. So the first thing we do in our test is get all our Python imports. First thing is importing Beaker itself, but then we also import our auction class that we made. So if you remember, in our contract itself, we had a class called auction, and in our test, since we want to interact with that contract, we need to import it. Then we also import some various functions from the SDKs, and I'll go over what they do when we encounter them. And then finally, we import PyTest itself for actually executing the test. Okay, so this is our first fixture. And for those that aren't familiar with PyTest, you have fixtures and you have tests. And fixtures are basically like helper functions that help you initialize state to what you want it to be when you're ready to actually test. So here in our create app fixture, we basically want to write code that creates the application that we can then use in our test. So the first thing we do, we're going to create some global variables that we're going to use throughout the test. If you really wanted to avoid using global variables, you would probably want to use fixtures and properly, pass down the values. But in this case, it's just a little bit easier to use global variables. So that's what we did here. And then the first thing I do here is I use this sandbox.getAccounts. And this is kind of the first that really alleviates the need for running our own helper function. So what the sandbox.getAccounts function does is get all the accounts on our local network and then gets their values. So this specific array is going to be sorted by the amount that the accounts hold. So basically this will be a sorted array ordered by the amount that the accounts are holding. And then now what we want to do is we just want to pop off one of those accounts, and we use that account as the creator for the application itself. And then now we're ready to instantiate the application client. So like I mentioned, the application client provides some abstraction for interacting with our application. So here what we do is we call client.applicationClient from Beaker, and we're specifying a couple things. The first of the client we want to use to interact and create the to create and interact contract. Here we're just using sandbox.getAlgo. This is just a helper method for getting the default sandbox connection information and connecting to AlgoD through that information. And then we're specifying what the app that we're creating the application client for is. So if you remember, we imported this auction class from our smart contract, and we're specifying the teal version as version 6. Then finally, we need to pass a signer, and what this is basically specifying is when we create the transactions with our application client, how do those transactions get signed? And of course, Beaker provides abstraction for handling that. So in our creator account that we popped off our array from .signer method, and this is a method that automatically sign transactions for that account. Then once we did a little bit of that setup, we .create. What that's going to do is create the application itself. Okay, so this is our second fixture. This is going to be initiating the start auction function. So what we're doing here is we're using our app client to, and if you remember, this was a global variable, so this is coming from that first fixture. What we're doing is getting suggested parameters. So when you make a transaction on Algorand, you get the suggested parameters, so you don't have to manually specify things like how long the transaction should be valid for and what the fee should be. The suggested parameters will calculate that all for you. So we get that from the application client. and then we're using the SDK to make a transaction, attach a signer to it, and then we just have one line here, appclient.call, where we're specifying we want to call the start auction function. We're specifying our payment argument is going to be that pay transaction we created. We're specifying our starting price is going to be 10,000 microalgo, and our length is going to be 36,000 seconds. And now we have a fixture for sending our two different bids, because the logic is a little bit different for both of them. We want to make sure we have complete code coverage. So here, for a fixture for our first bid, we're popping an account off the array to signify as the first bidder. We're getting our suggested parameters from the application client. We are creating a pay transaction, which will be the actual bid. So the starting amount is 10,000. We want an amount that's higher than that. So as you can see in our transaction, we're specifying the amount is 20,000, and then attaching our signer to it, and then we call the method with appclient.call, specifying we're calling the bid method, and then passing in the payment transaction, passing in the previous bidder, and attaching a signer to it. And then now we have our second bid, and this is very similar logic to our first bid. Really the main difference here is that when we send that second bid, we need to figure out who the first bidder was and add them to the application call so we can return their payment. So what we're doing here is we're getting our suggested parameters, but we're doubling our fee here. So if you remember, we set our inter-transaction fee to a hard-coded 0, and what we're doing here is doubling this outer fee so that that 0 transaction fee is made up for in this outer transaction call, which is why we're doubling it. And then what we're doing is we're also getting our first bidder amount. This is something we're going to be running an assertion on in our test later, so we want to save this before we execute this, because we want to make sure that the accounts are actually given the algo that they rightfully deserve. And then we make the bid transaction much like we did the first time. So creating the payment transaction using the SDK, and then calling the bid function, passing in that payment transaction and the previous bidder. And finally, we have our end auction fixture. And this is a little bit different. So we do the same doubling of the fee to cover that inner transaction. But one thing you might notice here is that we're not actually using Beaker, the appclient.call method. And the reason we're not using appclient.call is because this end auction functionality depends on the timestamp that we get on chain. The problem is, if we want our test to be quick, we don't actually want to wait that 36,000 seconds that we defined to be the length of the auction, right? You don't want to wait that long every time you test. So instead, you want a way that you can essentially spoof what the current timestamp should be read as during execution of the contract. So we use a feature of AlgoD, the node software called Create Dry Run. And what this basically does is creates a template of a transaction that is executed against the current state of the blockchain, but it's not actually added to the ledger. So what we're basically doing is like simulating what this transaction would actually do if we were to send it to the network. And one of the nice things we can do during this dry run is specify the latest timestamp. So if you see here, we have latest timestamp equals some super large number, and that signifies January 1st, 2050. So we're well beyond when the end of the auction should be. And this is basically going to ensure that when we call this end auction, we are indeed past that end time, and we actually trigger that end auction logic. And then so once we form the transaction or form the dry run, we then call appclients.client.dryRun. So we're still connecting to AlgoD through our app client, but we're just calling the dry run endpoint rather than .call. And then we are getting the global delta. And so what this basically is it's a summary of what global state has changed throughout the course of the smart contract execution. Okay, so now we can actually go into our actual assertions that we want to use for our testing. This is really kind of like functional regression testing. So we have some simple tests that verifying account balances and state. So our first one is when we create the application, we want to test that everything was initialized as we expected. So first thing we're doing is test create owner. We're verifying that when we create the auction smart contract, the owner is set to the creator address. Then we're going to test the highest bidder. We want to make sure that's an empty string. And then we test our highest bid auction end times values to be 0, because those are the default values that we expect them to be when we create the contracts. And now we have some assertions for when we actually start the auction. So after we call our start auction call, the first one we're doing is making sure that the auction end is not 0 and it was properly initialized. And then what we're doing is verifying that the highest bid is equal to the starter amount. So in our fixture, we specified the starting amount to be 10,000. So here we're just reading the global state of the application through Beaker and making sure that it is indeed 10,000. And that's an important thing to note here, is that getting the global state is just a single line call. It's just app_client.get application state. And this provides a ton of abstraction on a lot of manual things you have to do and getting it into like something human readable, whereas Beaker does this all for you, and we can just assert that it's equal to 10,000. And so now we're doing something very similar on our bids. So for our first bid, we're verifying that the bid amount is updated properly, much like we did when we started the auction. And then we're verifying that it saved the highest bidder. So we're verifying that the state was updated properly. And then now we have for our second bid fixture. So in our second bid, not only are we verifying that the state was updated as we expected it to, much like our first bid, but we're also verifying amounts of the accounts that are involved in this process have the balance that they expect. Right, so we're making sure that the first bidder balance, they get their first bid back. So here you'll see, if you remember in our first bidder fixture, we had this first bidder amount variable, and this was how much algo they had in their account, or micro algo they had in their account before sending the bid. And then we want to make sure that now, after sending the second bid, they have that initial bid value back. So they sent 20,000 as a bid, they should be getting 20,000 back when there's a new highest bidder. And then we're also doing the same thing for the contract. So we're making sure that the contract has the expected value in it. So we're making sure that it only has the 30,000 that we just sent as a bid, plus the 100,000 micro algo that was used to seed the account initially. And then finally, we have some assertions for the end. So the first thing we're doing is ensuring that the second bidder address, we're ensuring that the owner is set to the second bidder address when the auction ends. So when we call the end auction, there is a second bidder that has the highest bid. So the end auction will then change them to the new owner. We want to verify that that actually happened. And then we also want to be checking that the highest bidder is set to an empty string and our auction end is set to 0. So basically reinitializing those default values that we had. And again, if you remember, we used dry run here. So we're using this global delta variable that we got from the dry run when we sent it to our node. So that is what testing looks like using PyTest. You, of course, don't need to use PyTest. And we also have tooling for interacting with a Beaker smart contract on TypeScript or JavaScript, which I'll be going over for web integration. So you could write tests using a JavaScript testing platform, something like Jest, for example, is also an option. But now I'm going to be going over web integration. Right, so writing the actual smart contract is only like half of the story when it comes to writing a full-fledged DApp. You want a way to implement that smart contract into your web application, so you have a fully functional DApp that end users can actually use. So what's our end goal here? As you can tell, I am not a Web 2 dev, so we have a very simple interface here where we basically have a couple of buttons to initiate the various functions that we've created in our smart contract. And we want to be able to do all these things on testnet. So I'm going to be going over a couple of key things, going over like what it looks like, and then code, showing a little bit of that, and then going over a quick demo. But the first thing to mention is this tool. Basically does is it takes a Beaker smart contract and basically re-implements it in TypeScript automatically. So one of the artifacts of a Beaker contract when you execute it is this thing called the application spec. And this is basically a JSON file that specifies what sort of functions are in the smart contract, what the compiled code is, what are the types, basically everything you need to know in order to interact with the smart contract and recreate the smart contract itself. So we use that application spec to then generate TypeScript code. So here you can see I have a npm script just called Beaker. So I run npm run Beaker. It'll compile to generate that source code automatically. And once we have that source code generated, in our case, Beaker/auction client is where the generated code lives. So you can see here in our JavaScript file for our front end, we're just importing that auction class from that TypeScript file. So it's just a regular TypeScript class that we can import and use to interact with the smart contract. We also have some other imports, so algo SDK and myalgo, since we're going to be sending transactions on testnet. And since we're going to be sending transactions on testnet, by default, Beaker will just connect to a local sandbox. So instead, we want to create our own connection to a public API using algo node here that connects to testnet. So once we have that connection set up, we can start actually interacting with the smart contract. So this is a snippet from the JavaScript code showing over what it looks like when we create the smart contract. So we'll have a button that's just called create, and when we click that button, what we want to do is instantiate this auction class. So this is a class that was auto-generated by Beaker TS, and we're passing in some parameters here. We're specifying which client. We're specifying a signer function used to sign transactions, and I'll show you what that looks like using myalgo in the next slide. And then we're it from a drop-down menu. And finally, to create that, we just call auction_app.create, and it's an asynchronous call, so we have a wait there to make sure that we initiate those variables. And we are now ready to, and we have now, after this line of code, deployed the contract on testnet. So one of the input parameters to when we created the application client was this signer function. If you remember, there was a signer function in our PyTest, but that function was automatically given to us through the sandbox.getAccounts abstraction. In our case, we need to write our own signer function that lets the end user sign their transactions using myalgo. So here we have this myalgo.signTransactions function, which is basically a wrapper around the native myalgo APIs, and then we're using that to actually sign the transactions, and then we're returning the signed transactions. So this signer function, all Beaker is expecting is basically a function that takes in transactions and return those signed transactions. How you get from transactions to signed transactions doesn't matter to Beaker. That's why we can just write our own function that calls out to myalgo to sign those transactions. So we now have our application deployed. The end user has called .create, and they now want to do other things. In this example, we're signifying the start auction function, but it's a similar pattern for all the other all the other functionality as well. So what we're doing here is instantiating this auction class pretty much the exact same way that we did when we created the auction, but this time around we are specifying the app ID. So with a Beaker application client, you don't, it's not just used for creating the application, a brand new application. It can be used to interact with an existing application, provided you know the application ID. So here, that's what we're doing. We're telling this Beaker or this auction class that, hey, this is the app ID that we want to interact with when we're calling methods on it. And then, much like we saw in our PyTest, we're forming a transaction and then passing that as an argument, and then passing in our arguments to this start auction function. And the nice thing here is that you can see that the auction class, it's aware of what those arguments are. It's aware of what those types are. It's all auto-generated TypeScript that provides that sort of seamless experience of interacting with a smart contract like it's a regular JavaScript library. And that's the real value of this application client here. So if you want to learn more, this is a QR code that will send you to a link tree. It has the link to the repository for the Beaker auction. It also has a repository for Beaker and a link to our Discord. And so if you want to learn more, go there. And real quick, I will go over just an example of what this actually looks like when we serve the code. So if we do npm run serve, it will load our beautiful interface here. And so now what we can do, zoom in, make this a little bit bigger. So the first thing we're going to do is we can connect our wallet. And then now that we have our wallet connected, we're going to be using this Alice account, and we're just going to call .create. And that's going to tell, when we did that, that called that signer function and told us that we want to sign the transactions using myalgo. Give it a minute to create the application. It is an application that is actually deployed on testnet here, and we can take a look at our application state, and we can see we have all those keys that we specified in our Beaker smart contract. So now we can go here and we can start the auction. So we'll start it for 10,000 microalgo. So again, calling that signer function, signing with myalgo, and then we're waiting for that transaction to go through on testnet. And now we can see the auction has started. So if we go back over here and we reload, we now see that our values have been initialized, right? So we now have the highest bid to 10,000, and we have a auction end time. And now we can bid. So we can use this Bob account, send a new bid. And again, same thing as before, it's using that signer function to sign using myalgo. And we will see the new values populated in our global state. So we now see the 20,000, and we'll see that using Beaker and very few lines of code, we've been able to deploy a contract on testnet and easily interact with it in JavaScript using auto-generated code provided by Beaker TS. And this is really the value add of Beaker, right? This ability to have one smart contract code and then be able to leverage that same code base in Python tests and JavaScript tests and JavaScript front ends, Python front ends, you name it. This is what the application client can provide for you. Okay, so that is all the content to go over. I'll bring this up on the screen. If anyone else is interested in the resources, are there any questions?
All right, here we come. Question time.
Thank you. In that bid function that you showed us before, there was an argument for highest bidder or previous bidder, something like that. And I'm wondering just the logic of when you're bidding, like you're a third party or whatever other account, why do you care to send the highest bidder? Doesn't that live in the global state? And I'm just wondering why that structure.
Yeah, so let me see if I can go back to that. So the reason that we have to pass in the the previous bidder argument here. So the reason we're passing that in is because we're sending a transaction to that previous bidder to return their bid. And you might ask, why can't you just read that from global state when we do that? And the reason is because on Algorand, you need to predefine any accounts that you're sending a transaction to. And so like when you send a transaction to a node, it sees which accounts it's going to be interacting with beforehand and load it off disk into memory. So during the actual execution, it's not actually reading out to disk, it's just reading that account state from memory. But it needs to know before actual execution what accounts it's going to be touching. So we're passing that as an argument here to let the AVM know, hey, we're sending a transaction to this account, we need to update its state, preload this into memory. If we didn't pass in this argument, what would basically happen is the AVM would panic and say, hey, you're trying to touch account that you basically don't have permission to touch. And it would panic and the transaction would fail. So that's why we need to specify it as an argument rather than just reading from global state during execution.
Do we have any more questions? Oh, good. We're coming.
I do have a question about the start auction function. I do believe there was no checking there who is actually calling that function. So I might start an action as a Bob, maybe. Is that correct? So I might start the auction not as an owner of an auction. Or was there checking? Was the code checking for who is signing the transaction?
Oh, okay. So you're saying in this, sorry, it's a little hard to hear. So you're saying, like, is there code to like assert that the owner is actually the one starting the auction?
Yeah, that's the question.
Yeah. So there's actually not, but there should be. So one of the things that I forgot to include here is if you saw Chris Kim talk earlier, Beaker has a authorize decorator, and so on this, like before this line at external, there's a decorator that will specify that only the current owner can call this function. So you can write function to do that. I just forgot to show it here.
Okay, thank you.
Yep.
Do we have any other questions? And that was a good catch out there. Nice work. Nice. All right, everyone. Well, Joe Polny, my esteemed colleague here, giving us the example of the application written in Beaker. Nice work there.